chemistry Ado. Uh, Today we'll be starting with A levels chemistry, specifically organic chemistry. We'll be starting off with that. So essentially speaking, there are three parts of AS or A level chemistry. The first part is the physical chemistry. The second part is the inorganic chemistry, and the third part is the organic chemistry. So, having said that, uh, let's have a little introduction of what organic chemistry is for A levels chemistry. Okay. Organic, in general, is the chemistry of carbon, and to essentially speaking, all organic compounds contain carbon. But it is also important to note that not all carbon containing compounds are organic, right? So let's be very clear on this. So all organic compounds do contain carbon, but not all carbon containing compounds are organic. So it's essentially a very important point. So all organic compounds have carbon, but not all carbon compounds are organic. Very important point. Alright. So it all started back in the 17th and 18th century. We used to have a vital force theory which said uh, that we cannot make organic compounds in the lab, and there is a unknown vital force that is required for the formation of organic compounds. That is when the search for organic compounds started. That theory was eventually discarded when we first formed urea in the lab, and since then we have made millions of organic compounds. So, with that little introduction, we need to understand why carbon is so essential, and why carbon is the basis or the central element for whole of organic. So the thing is that carbon shows three types of hybridization, and that is one of the most important points for the existence of carbon in the for the centrality of carbon in the organic chemistry. So carbon exists in three states: sp1 or sp3, sp2, and sp. Right? When we're talking about sp3 hybridization, we're talking about carbon making single bonds with other elements. When we're talking about sp2 hybridization, we talk about carbon making double bonds with other elements. And when you're talking about sp hybridization, we're talking about a triple bond. And this ability of carbon to show all these three types of hybridization is essentially one of the reasons it's so central in nature. Now, we'll move on to some properties that some organic compounds share, which are central to all organic compounds. So let's see the properties of organic compounds. First of all organic compounds contain carbon. So all organic compounds contain carbon. Very important point. Next, all organic compounds are covalent compounds. They are not ionic compounds, they are covalent compounds. Right? So all organic compounds are covalent. Organic compounds covalent. Very important point. Next, all organic compounds are combustible or they are flammable. Okay, they burn in oxygen. So all organic compounds are flammable. All organic compounds are flammable. Right? Next, all organic compounds, essentially speaking, are non-conductors of electricity, but we have some organic compounds which are the conductors of electricity as well, which are conducting polymers, and we'll be studying them in this syllabus. So all organic compounds are non-conductors of electricity, are non-conductors of electricity, except of course the exception I've named, that is conducting polymers, except conducting polymers, right? As simple as that, right? So these are a few properties of organic compounds that in my opinion, every student of A level should know before we start with the in-depth analysis of organic chemistry. So now that we have some general properties in mind, we'll be starting with what is a homologous series. So what is a homologous series? So when we found the elements in our physical chemistry, we arranged them in order of their atomic number, right? And we found out that certain elements share certain chemical properties, and we arrange them in similar groups, right? And we noticed that in elements in a similar group share the same number of valence electrons, right? So that is how things happened in our normal chemistry. But what happened when we went to organic compounds? So when you're talking about elements, there are only a few hundred elements there. 137 is the limit of the number of elements that we can have. But when it comes to organic compounds are millions in numbers. Everything around you is organic. And there are millions of organic compounds that can be formed. So it was, if we were to name them randomly, like we named the elements, hydrogen, lithium, beryllium, having no relation whatsoever to their properties, it would have been very cumbersome to remember all the names of all the organic compounds. So we started arranging them in series, or something equivalent to groups in the periodic table. So we named those series the homologous series. So all members of homologous series have the same chemical properties. So all members of a homologous series have the same chemical properties. Have the same chemical properties. Great. Now, having said that, there are some other properties that members in the homologous series share. The second one being they have the same general formula. Same general formula. And when we get into detail of what a general formula is, you'll be more clear. But for now, just note that they have the same general formula. Next, so when we're talking about groups, right? When we're talking about elements and the groups, elements in a group share same chemical properties because they have the same number of valence electrons, right? Similarly, members of a homologous series share the same chemical properties because they have the same functional group, right? So try drawing that analogy, so it makes stuff clear in your mind. So they have the same functional group, right? And what you'll notice is when we get to homologous series that each succeeding member differs from the preceding member by a CH2 group. So each, and I'll give you an example to clear this out. So each succeeding member differs from the succeeding member by CH2 group. And the molecular formula for a CH2 group, essentially speaking, is 14. So Each member has a difference of 14 from their preceding member. I'll give you an example. So we have this homologous series known as alkanes. It has this functional group of CH. It has this first member of CH4. The next member would be if I add a CH2 in it, and that would make 2 carbons, C2, and total of 6 hydrogens. So the next member would be C2H6, and the next member would be if I add another CH2 group, so 3 carbons, C3 and H8. Okay, so that is how you notice how they differ. How the succeeding member differs from the preceding member. As far as the syllabus of A level and AS level is concerned, we have quite a few homologous series that we need to discuss. The first ones are alkenes. Before them are alkanes. Of course, we need to discuss alkanes before alkenes. Then we have alkynes. The next one are haloalkanes. Nitriles. You don't need to worry about the names right now. Just as an introduction of what we'll be studying. You have alcohols. You have ether. We have ester. We have carboxylic acid. We have carbonyl compounds. We have arenes. We have amides. We have amines. And we have acyl chlorides. Out of these series, arenes, amides, amines, and acyl chlorides, they're all A2. They're all part of A2 examinations. The rest are part of your AS. More importantly, alkynes and ethers, right? Both of these are not as such part of your syllabus, but they are on the outskirts of your syllabus. So I'll be discussing them as well. So having said that, let's move on to the functional groups in our next video, of course. But it's very important before you watch the next video to understand everything we have done so far. So it's important to know what a homologous series is, and it's important to know what functional groups are and what are some properties of organic compounds. If you're clear with that, we can now move forward with functional groups as a whole.